This video is a step-by-step solution for the example entitled Evaluating Minimum Theoretical Compression Work. In this example, you will learn about analyzing the adiabatic compression process of refrigerant R134A in a closed system. In this example, you will also learn how to compute the minimum theoretical work for this process. Let's look at the problem statement as given to us. Refrigerant 134A is compressed adiabatically in a piston cylinder assembly from saturated vapor at 10 degrees F to a final pressure of 120 pounds per square inch. Determine the minimum theoretical work input required per unit mass of refrigerant in BTU per pound. First, let's do a critical read of the problem statement, highlighting in red the important information given and in green the information requested. Highlighted in red for the information provided, we have the following. Refrigerant R134A is compressed adiabatically in a piston cylinder assembly from saturated vapor at 10 degrees F to a final pressure of 120 pounds per square inch. And highlighted in green for the requested information we have, determine the minimum theoretical work input required per unit mass of refrigerant in BTU per pound. Let's start to develop the solution. The first thing to do in any problem solution is to summarize what is known. This is essentially the same information we highlighted in red in a critical read of the problem statement, presented here in a compact bulleted list format. Refrigerant R134A is compressed without heat transfer from a specified initial state to a specified final pressure. The next thing to do is to summarize what we have to find. This is again the same information we highlighted in green in a critical read of the problem statement, presented again as a bulleted list. Determine the minimum theoretical work input required per unit of mass. The next step in the solution is to develop a relevant schematic. In this case, it was provided to us. However, let's highlight a few important pieces of information that were provided, which will help develop our solution. The first thing to note is that there is no mass entering or leaving the piston cylinder assembly. This immediately suggests that a closed system approach is the correct one. Having recognized this important fact, let's select our system boundary. In our case, it is selected to enclose the R134A in the cylinder and follow the physical boundary of the piston cylinder assembly as delineated on the schematic with the red dashed line. The schematic clearly shows the substance being compressed, here refrigerant R134A, and the minimum work to be applied to the piston to compress the refrigerant, which is to be determined. The next step is to develop the appropriate thermodynamic diagram to represent the process, in this case the TS diagram. Let's highlight the diagram with the information provided. State 1 is a saturated vapor state at the right edge of the vapor dome and at a temperature T1 is equal to 10 degrees F. From this state, it is compressed to a given pressure, P2 is equal to 120 pounds per square inch. The best scenario to compress the refrigerant from 1 to 2 is to undergo an isentropic compression process from 1 to 2s. Hence, the specific entropy does not change during this process, since and S1 is equal to S2s. The process is represented by a vertical line on a TS diagram. The process from 1 to 2 is the actual compression process, where S2 is greater than S1. All accessible states are to the right of the isentropic process line on the TS diagram, indicative of a specific entropy increase. It is important to realize that the minimum compression work will correspond to the lowest internal energy state at 2 and will be achieved by the isentropic compression process from state 1 to state 2s. The next step is to develop an engineering model, which is a set of simplifying assumptions which will allow us to perform the analysis of the problem. The refrigerant 134A is a closed system. There is no heat transfer with the surroundings, and the initial and final states are equilibrium states. There is no change in kinetic or potential energy between those states. Having completed all the preliminary steps for our solution and represented the process on a TS diagram, let's develop the analysis. We can obtain an expression for the work using an energy balance for the system. Delta U plus delta KE plus delta PE equal Q minus W. By applying assumptions 2 and 3, the kinetic and potential energy changes drop out, and so does the heat transfer Q as the process is adiabatic. Dividing by the mass, we get an expression for the work per unit mass. Minus W over M is equal to U2 minus U1. We can obtain the specific energy U1 from the saturation table for refrigerant 134A as U1 equal 94.68 BTU per pound. Since U1 is known, the value for the work input depends on the specific internal energy U2 at state 2. The minimum work input corresponds to the smallest allowed value of U2 determined using the second law as follows. By applying an entropy balance on the closed system, we get delta S is equal to integral of from 1 to 2 of delta Q over T at the boundary plus sigma. Here, the entropy transfer term by heat transfer is set equal to 0 because the process is adiabatic. Thus, the allowed final state must satisfy S2 minus S1 equals sigma over M, which is greater or equal to 0. The restriction imposed by the inequality just shown can be interpreted in the TS diagram, as was shown earlier. Since the entropy production sigma cannot be negative, the value of S2 cannot be less than S1 as the process is adiabatic. When irreversibilities are present during the compression, entropy is produced, so S2 has to be greater than S1. The state labeled 2S on the diagram would be attained in the limit where irreversibilities are reduced to 0. This state corresponds to an isentropic compression, which also will correspond to the minimum theoretical work. By inspecting the table of superheated refrigerant R134A, we see that at constant pressure, the specific internal energy decreases when the specific entropy decreases. Therefore, the smallest allowed value of U2 corresponds to the state 2S. By interpolating in the table at 120 psi with S2S equal S1 equals 0.2214 BTU per pound Rankine, we find that U2S is equal to 107.46 BTU per pound, which also corresponds to a temperature at state 2S of about 101 degrees Fahrenheit. The minimum work per unit mass can be evaluated as follows. Minus W over M minimum is equal to U2S minus U1. Substituting the values for the specific internal energy in the equation gives us a minimum work per unit mass of minus 12.78 BTU per pound. This is the minimum theoretical work input per unit mass which we are seeking. The minus sign shows that work is being done on the system. As a final comment, the effect of reversibilities exacts a penalty on the work input required. A greater work input is needed for the actual adiabatic compression process than for an internally reversible adiabatic process between the same initial state and the same final pressure. Quick quiz. If the refrigerant were compressed adiabatically to a final state where the pressure P2 is equal to 120 psi and T2 equal 120 degrees Fahrenheit, determine the work input in BTU per pound and the amount of entropy produced in BTU per pound Rankine. You may want to stop the video at this point to work out the solution. The answers are 17.16 BTU per pound for the work input and 0.0087 BTU per pound Rankine for the entropy increase, both per unit mass. Hopefully, those are the answers you obtain. If not, review all the steps in this video and your calculations. If you are still having problems matching the answers, here are a few hints. Since the temperature T2 is specified, the process from 1 to 2 is not isentropic, and the exit property at state 2, U2 and S2 must be found. From the table of properties of superheated refrigerant R134a vapor at P2 equal 120 pounds per square inch and T2 equal 120 degrees Fahrenheit, U2 is equal to 111.84 BTU per pound and S2 is 0.2301 BTU per pound Rankine. As before, the work input per unit mass is given by minus W over M is equal to U2 minus U1, and the amount of entropy produced is given by sigma over M equal S2 minus S1. The numerical evaluation of those two expressions with the properties listed above is left as an exercise. Note that sigma over M is greater than 0, indicating that the process from 1 to 2 is not isentropic and entropy is produced due to the irreversibilities in the process. In closing, in this example, we have learned about analyzing an adiabatic compression process for R134a in a closed system. We have also learned how to compute the minimum theoretical work for this process. This concludes the step-by-step solution of the example entitled Evaluating Minimum Theoretical Compression Work.